Alrighty. Good morning, everybody, and welcome back to Calc 3. Plan for today, you're going to finish off Standard 15 by looking toward the second half of the integration packet, talking about a few more advanced problems today. And then if we have time towards the end of class, we'll start looking at Standard 16 and talk a little bit about polar coordinates and how they can be used to help integrate. As far as homework goes, on Friday, we will have a quiz on Standard 15. And as far as office hours go, I've got my usual office hour tomorrow afternoon, or not tomorrow afternoon, this afternoon from 2 to 3. Tomorrow morning at 10 and tomorrow afternoon at 1. Tomorrow morning I'm going to have to cut my morning office hour a half hour short because of, got to get ready for convocation for the spring. That will be a thing. Just got graded your exams, got them back. I have not updated Blackboard yet with your exam totals, or with your mastery totals from the exam, so I'll probably get to that in the next couple of days. But there's still a couple students who haven't taken the exam yet, so I haven't posted solutions quite yet, but once they do, I'll put solutions up on Blackboard. In the meantime, if you have any questions about your exam or anything you'd like to talk about, be happy to meet with you in office hours, or you can always send me a question by email. Any questions or comments before we get started for today? So, one day, the local cannibal is feeling a bit hungry and goes to the butcher shop and asks for some brains. So the butcher says, all right, I've got mathematician brain for $1 a pound, engineer brain for $2 a pound, and politician brain for $10 a pound. Cannibal's a little surprised by this. Like, wow, why does politician brain cost so much more than the mathematician brain? Is the quality of brain that much better than the politician? The butcher says, no. It just takes a lot more politicians to make up that pound of brain. All right. So you may recall, last Friday we talked about how to integrate to multivariable functions, where specifically we were looking at double integrals for how to find volume under functions going from R2 to R. So functions whose graphs are in R3. And so I thought we'd start off by doing just a quick little bit of review by looking at an example where we find the volume of a D4 dot. So, question. Any of you out there Dungeons and Dragons players? No? So, if you've played certain types of games, you might see four-sided dice, tetrahedrons. So today, I want to start with an example where we actually find the volume of one. See how much space does it occupy. So, we're going to set this up. We're going to have our x, y, z, 3 space. We're going to set it up so that we go 1 unit out in the positive x, the positive y, and the positive z direction. Kind of take the diagonals between each of these. And we're going to find the volume of what one of these D4 dice might end up looking like. And the way we're going to do that is we are going to integrate the function g of x comma y equals 1 minus x minus y over the region D given by the set of points x comma y, where x is going to go from 0 to 1 minus y, and y is going to go from 0 up to 1. So it turns out if you take this if you take this function, g of xy, which actually defines a plane, set it up like this, and you look at the volume under this plane over this particular region, y is going from 0 up to 1, x is only allowed to go from 0 up to 1 minus y, then that's going to give the volume of this space, which looks a lot like a D4 dot. So, I would like to set up a double integral to make this happen, where we're going to have an integral of the function 1 minus x minus y. So, based on what we said last Friday, which should we integrate first with respect to x over this region, or first with respect to y, do you think? Lori?
I think we should integrate with respect to x first, because the bound for x has a y in it.
Yeah, so we need the inside integral to be the ones whose bounds include variable expressions. Like we said last Friday, our outer integral, the bounds need to go between two constants. So I think I agree with Lori here. We want our outer integral to be the integral with respect to y, and our inner integral is going to be the dx integral. So we're going to integrate 1 minus x minus y from x equals 0 to x equals 1 minus y, and then from y equals 0 to y equals 1. I need an antiderivative of 1 minus x minus y taken with respect to x. So what would we get if we integrated 1 minus x minus y, treating x as the variable and y as a constant in this case? Emily? Say that again?
Oh, it's x minus 1 minus x. And then minus 1.
I'm going to write it as xy because I like alphabetical order. Now, if y is just a constant and x is our variable, then integrating will give us an x minus a 1/2 x squared minus x times y. So we're going to need to plug in 1 minus y and 0 here. Are we going to plug in those values for x or for y in our expression when we subtract? Holly, what do you think?
Just with respect to x.
Why x?
Because we integrate x.
Yeah, I agree. We just took an antiderivative with respect to x, and therefore when we plug in our bounds, we need to plug those into x, not to y. So when we do that, we'll get 1 minus y minus 1/2 times 1 minus y quantity squared minus 1 minus y times y, because why not? All of that minus what we get when we plug in 0, which is just going to be 0 minus 0 minus 0. Whew. All right, well, when we expand this outwards, we're going to get 1 minus y. Let's see, 1 minus y, the constant term is going to be 1 when we square this, so we'll get minus 1/2 times 1. Minus y will give us a negative 2y here, which negative 2y times negative 1/2 will actually give us a positive y. And then negative y times negative y will give us a positive y squared times negative 1/2 will be minus 1/2 y squared. We multiply this out, we'll get a minus y plus a y squared, all integrated with respect to y, which we can actually simplify a fair bit. Swoosh, swoosh, the minus y and the plus y terms will cancel out. The y squared terms, we have a plus y squared, a minus 1/2 y squared, so that'll come out to a positive 1/2 y squared. We have just a single minus y term, and the constant term is going to be 1 minus 1/2, which will be plus 1/2. And we end up with an integral from 0 to 1 of 1/2 y squared minus y plus 1/2. Someone give me a antiderivative with respect to y this time of 1/2 y squared minus y plus 1/2. Luke?
Let's see. 1/6 y to the third minus 1/2 y squared plus 1/2 y plus c.
And plus a constant term, but since we're doing a definite integral, we don't really have to worry about the plus c. If this was an indefinite integral, we would, but definite int, we can just plug in the bounds to this expression. Well, let's see. Do I agree with this? We differentiate, we'll get 3/6y squared, so 1/2 y squared minus y plus 1/2. I like it. And now, when we plug in our bounds, 0 and 1, we'll get 1/6 times 1 cubed minus 1/2 times 1 squared plus 1/2 times 1 minus a bunch of zeros. And finally, when we simplify, these will cancel out because they're both negative and positive 1/2. Turns out the final answer is going to be 1/6. So it turns out that if we have a D4 die that extends out 1 unit in the positive x, y, and z directions like this, the volume turns out to only be 1/6 cubic unit. Sort of integral we were looking at the end of class on Friday, where the inside integral has to be x here because we've because our bounds on x have an expression of y in them, whereas y is just going between two constants. And as we said last week, if you have the outside integral always has to go between two constants. If we wanted, we could rewrite this set to let in a different way to let x go between two constants and y go between expressions of x, and then we could integrate with respect to y first. But the way that this set was written, we had to integrate it like this. Any questions or comments? Yeah, you go.
We're rewriting the bound so that x is as constants.
Yeah, sure. You can do that. Always, every time I go to the board in this class, it's always dry. Someone has dry erasers up there. So let's actually do that really quick. So I'm going to graph out just this set of points in R2, where that was scary. Where we have that y is going to go from 0 up to 1. X is going to go from 0 to 1 minus y. So I'm going to get something like this, I believe. Because let's see, x equals 1, then y will be 0 here. And so the set that we're going to be integrating over, let's see, y is going from 0 up to 1. X is going to go from 0 to 1 minus y. So we're actually going to be integrating over this region here. Since y goes from 0 up to 1, x goes from 0 on the left to the line x equals 1 minus y on the right. And we'd like to be able to rewrite this set of points so that x is going to go between two constants now, and y is going to go probably between some expression in terms of x up to a constant. So how can we write this so that x is going between two different constant values, according to our graph of this set right here? Well, in other words, if you look at this set, what's the leftmost x value in the set, and what's the rightmost x value in the set? Yeah?
It'll be from 0 to 1.
Yeah, it looks to me like x, in this case, we could write as going from 0 to 1. And then y is going to be a little bit trickier. Looks like y is going to go up to 1 on the top. So we can say y is going to be less than or equal to 1. On the bottom, though, our y coordinates are going to have to be above this line right here. So right now, we have this line written as x, as an x equals expression in terms of y. What would be another way that we could write this line as y equals some expression in terms of x? Meaning, in other words, if x is equal to 1 minus y, what would y have to be equal to? Let's go with Jack.
Negative x plus 1.
Yeah, negative x plus 1. And since I like the symmetry, this I'm going to write it as 1 minus x. So I think this could be a way that we could do that. To answer your question, Jacob. We could write it as the set of points x comma y, where x is going to go from 0 to 1, and y is going to go from 1 minus x up to 1 in this particular case. And then if we wanted to, we could rewrite our initial integral as something like integral from 0 to 1 of the integral from 1 minus x to 1, and then integrate with respect to y before we integrate with respect to x. And assuming we do everything correctly, we should then end up at the same final answer of 1/6. We did this. There questions or comments? So let's take a look at another example. And this one's going to get a little bit more interesting. So this time I want to integrate from y equals 0 to y equals 2, from x equals y over 2 to x equals 1, the function e to the negative x squared. Integrate with respect to x, and then integrated with respect to y. So how would we start by integrating e to the negative x squared with respect to x? Let's see, who needs to be cut down in size? Yeah, I'll go with you.
Okay.
How would you integrate e to the negative x squared with respect to x?
Well, I know that if I'm finding the derivative, I would pull out the exponent and multiply it by e and then keep the same exponent because it's an e function. So I can divide the function by the derivative so that when I multiply it out, it'll cancel out and I get the function I have now.
Ooh, okay. So what would that give you if we did that?
It would be e to the negative x squared over negative 2x.
Like that? And so this would be something where if we differentiated, the negative 2x would come down and cancel out. One problem I have with that.
Okay.
I think if we wanted to differentiate that, we would need to use the quotient rule, since we have an expression of x in the top and bottom, and then it wouldn't actually work out that way. That would be nice if it did, but it doesn't quite work out. So, let's see. It's not going to be so simple as using, say, reverse power rule to integrate e to the negative x squared with respect to x. We could try and do a u substitution.
Oh, yeah.
It wouldn't work. We could integrate by parts. It wouldn't work. We could do an inverse trig sum. It wouldn't work. We could do partial fraction, decomposition. Wouldn't work. Turns out there are no Calc 2 techniques, or really any good techniques in general, for integrating e to the negative x squared with respect to x. There is actually a function that is the antiderivative of e to the negative x squared with respect to x. It's called the Erf function, or as I like to refer to it, Erf. It is not a nice function. It is not something that you can easily write out very nicely. Basically, what I'm getting at is we can't integrate e to the negative x squared with respect to x. Sorry to pick on you a little bit. That was a good idea. I think that was a good idea. The issue is the quotient rule would not really agree with it. So we cannot integrate e to the negative x squared with respect to x. What could we try doing instead? Huh? Yeah, e to the negative x squared with respect to x is really hard. Emily, how would you take integral of e to the negative x squared with respect to y?
So you have to change the constraints first. And so if x is equal to,
Just tell me what the antiderivative will be. We'll change the constraints here in a second.
e to the negative x squared y.
Yeah. E to the negative x squared is hard to integrate with respect to x, but it's easy to integrate with respect to y. Because with respect to y, it's just a constant. And integral of constant with respect to y is just going to be that constant times y. So, Emily, I think I like your idea here. What we can do is, we can't integrate this as is, but if we can swap the order of integration, this is, I think, going to be a lot easier to actually go through and integrate. So let's try that. So, as is, our set of points for integrating over is xy, where y is going from 0 to 2, x is going from y over 2 to 1. If we graph that out, that's going to give us a set of points where, let's see, y will go to 2, x will go to 1. I think we're going to get this. If x is going from y over 2 on the left to 1 on the right, and y is going from 0 up to 2, looks to me like this is going to be the triangle, in this case, that we'll be integrating over. X over 2 on the, y over 2 on the left, 1 on the right, 0 on the bottom, 2 up top. And I think what we'll have to do is to rewrite this, similar to what Jacob was asking us to do in the last example, rewrite this so that now x is going to be going between two constants and y is going to be going between two different potentially expressions in terms of x. Olivia. So looking at this graph, how could we let x just go between two constants here?
You could say 0 is less than or equal to x plus less than or equal to 1.
Yeah, I like that. 0 on the left, 1 on the right. I think for y, we'll have to let y be greater than or equal to 0 on the bottom, because the bottom is just this flat edge, y equals 0. How could we rewrite this for y less than or equal to something? Jackson? 2x. What makes you say that?
Like the algebra, if you look at the algebra, the graph looks like that was something like the line y equals 2x.
Yeah, in fact, it is the line y equals 2x. If we just rewrite the equation x equals y over 2 and solve for y, we get that the line x equals y over 2 is the same as the line y equals 2x. And I think I agree with you, Jackson. That's going to be another way that we could write the same set that we're integrating over, except this time x is going to go between two constants, y is going to go between constant and expression in terms of x. And now we should be able to rewrite our integral so that we're integrating with respect to y first instead of with respect to x. In fact, we're going to have an integral from y goes from 0 to 2x. X is going to go from 0 up to 1. And now, Emily, can you remind us what you said, what we would get if we anti-differentiated e to the negative x squared with respect to y? We're just going to get e to the negative x squared y. I'm going to write it as y e to the negative x squared. Evaluated from 0 to 2x. Hard to integrate with respect to x, much easier to integrate with respect to y. So if we keep going, we can go ahead and plug in our bounds for y. That'll give us an integral from 0 to 1 of, let's see, 2x e to the negative x squared minus 0 e to the negative x squared, which turns into just being an integral from 0 to 1 of 2x e to the negative x squared, where we have to integrate this with respect to x. Okay, Brianna, I'll give you another chance here. At this point, we have to integrate with respect to x. We've already integrated with respect to y. We have no choice now but to integrate with respect to x. Any idea of how we might do that in this case?
We can do the same process that we did before. So we know that if we take the derivative of e to the negative 2x, you would get negative 2x e to the negative 2, or e to the negative x squared, you would get negative 2x e to the x negative x squared. So you can deduce from that your integral would be negative e to the negative x squared.
Oh, you want to skip straight past the having to go through the tricky integration technique and go right to the answer, huh?
Yes.
You're absolutely correct. But let's say you didn't recognize that right away, what it was going to be. What Calc 1/2 integration technique could we use in order to get out this, that it comes out to negative e to the negative x squared?
That would be the reverse power rule. Or the power rule,
Technically, sort of.
kind of.
Lori?
Substitution.
That's what I was going for. Yeah, we could use U substitution here, and then you're right, we will end up, well, actually it's not going to be reverse. Well, technically it is going from 2x to x squared, but U substitution, I think, is kind of going to be the easiest way to evaluate this integral. So Lori, what would you like U to be in this case?
Negative x squared.
Negative x squared? I can get behind that. So if U is negative x squared, what will we get for our du dx?
Negative 2x dx.
Just negative 2x, and then when we move the dx term over to the other side, we'll get negative 2x dx. I see that we have a positive 2x dx, so I'm going to rewrite this a little bit to get negative du is 2x dx. And then we can rewrite this integral now to be in terms of the variable x instead of being, or in terms of u, sorry, rather than being in terms of x. We can replace e to the negative x squared with e to the u, and we can replace 2x dx with negative du. And we end up with just an integral from x equals 0 to x equals 1 of negative e to the u du. What would we get if we integrated negative e to the u with respect to u? Integrating e to the u is just going to give us e to the u, and the negative sign comes along for the ride. So we get negative e to the u, evaluated from x equals 0 to x equals 1. What do we need to do with this expression before we plug in 0 and 1?
We can either adjust the bounds for u, or we can turn e to the u back into express in terms of x.
Yeah, right now we have a disconnect where we have an expression in terms of u and bounds in terms of x. So we either need to plug back in our x expression here to get everything in terms of x, or get our bounds to be in terms of u. Which do you want to do?
I'd probably just change the bounds.
Oh, I don't like that. I'm going to rewrite it in terms of x, because that feels like a little less work. To be fair, there's nothing wrong with that, and if you did that on a quiz or something, that would be totally acceptable. Use negative x squared. I want to write this as negative e to the negative x squared. Only to mainly point out that, yes, Brianna, I think you were absolutely correct. You just skipped straight from this step to that step without doing the substitution in the middle. And now we can actually plug in 1 and 0 for x, and we'll get negative e to the negative 1 minus negative e to the 0, which is going to be negative 1 over e plus e to the 0, which is just going to be 1. So I think we're going to get a final answer of negative 1 over e plus 1. Or if you prefer, you could write that as 1 minus 1 over e. This one was a bit tricky. Let's summarize up. Sarah, what made this integral trickier than the D4 integral we did at the start of class?
The fact that the first setup we had was so tricky, we had to switch up the constraints.
Yeah. E to the negative x squared we couldn't integrate with respect to x. So we had to swap the order of integration to make it work out. Jacob had asked us about how could we swap the order of integration in the first integral, which we did, but in the first integral that was optional, switching up the order of integration from how it was originally given. In this case it was mandatory because we couldn't integrate e to the negative x squared with respect to x. We had to integrate with respect to y, and then when we got to this step, 2x e to the negative x squared, that was actually a lot easier to integrate with respect to x because we could do this u substitution. Dr. Gerstle, are you going to make us do all of these Calc 2 integration techniques like integration by parts and stuff? Nah. I might give you some problems where you have to do u substitution, but you're not going to have to do integration by parts or trig subs or partial fraction decomposition in this class. Theoretically, you could if I gave you a problem like that, but I don't plan on it because that's kind of integration techniques is more of a Calc 2 thing for those types of techniques. What I'm more interested in here is how can we do things like swap the order of integration to make our lives easier. Any questions or comments about this example? In that case, I have an example I'd like for you all to spend a few minutes working on. I want you all to take just a few minutes and do this, and you're welcome to work with your neighbors on this if you'd like. I want you to integrate from 0 to 2, from y squared to 4, the integral of y cosine of x squared integrated with respect to x, integrated with respect to y. Go ahead, take a few minutes, and see if you and evaluate this integral. And as always, you're welcome to work with the people sitting around you, or you're free to flag me down and ask questions. I'd like to see you evaluate this integral.
That's what I'm thinking about, yeah.
If it helps, I'll draw out the region we're integrating over. Y is going from 0 to 2. So I picked one of those. Did exactly what I wanted.
Yay.
Forget if you're feeling stuffed or you're not quite sure how to get started with this one, feel free to raise your hand and flag me down, or you can ask someone sitting around. I think what you should do is you would have to rewrite your set of points. So instead of y1 between two constants, x1 between expression x y. See if you can rewrite the set of points for integrating over so that the x is going between two constants and y is going between. If you can do that, then you can swap these in order of integration. Yeah. I think your issues will come in some ways. But you're close. Not really. If it was cosine squared of x, then there's more you can do. But
That's what I was.
with cosine of x squared, there's nothing. I will say this: if the question you're asking is this possible to solve without swapping the order of integration, I
Should be
think the
one
answer
fourth
is yes,
because
but
it's
that dives deep into trig identities I don't really remember very well. Trig identities I've probably seen at some point, like maybe 10 years ago, but I don't really want to dredge up here how to hold it.
cosine of x. And you use some.
I forgot you said this is so that's
So you're going to have x cosine of x.
I guess I haven't.
Calc 2 is such a fever dream.
Yes.
I feel you.
Awesome.
Yeah. I took it with Dr. Mann. It was really awesome, but it was a weird class. It was just, I feel like nothing was cohesive, and it was all like, you're wearing this, and then you're wearing this, and you're wearing this, and you can't put them together.
That's the problem with Calc 2. I think that's not specific to how Dr. Panaggio taught it. I think every Calc 2 teacher has run into the same issue, and that Calc 2 is sort of just a hodgepodge of topics.
Yeah, that's exactly what happened. He gave a good analogy. He's like, okay, you're adding this to your toolbox. Oh,
Yep.
that's it. Alright.
So I heard what I just took out. Alright, let's take another minute or so, and then we'll come back together as a class and look at this together.
So it's I'm sorry, science in code 16. 35 answer. There's one.
It's just setting up how you rewrite this. Well, let's think of it this way. So you want the x to go between two points, right? So what's the left hand x coordinate? X can be
But that's.
I forget.
What am I?
Yeah,
How about y?
probably two. I remember making flowers.
So I was like, there's no two.
looks like it's going from a constant value on the bottom to something
I'm like, what's going on? What's wrong with you?
that on the top and on the bottom.
Okay.
For plugging
Yeah.
Oh.
Negative that because I guess it's good. So I think the issue is you can't actually. That's not actually being right. I think what you have would violate the product. Because you integrate like if you multiply this out, and then if you do the product rule to integrate this or to differentiate this, you're not just going to get y cosine x squared. You're going to get something a little bit nastier.
Yeah, we could do
You get a sine of x squared and a cosine of x squared. But again, this is not going to be good. Imagine you could do something similar to what we did in last time.
Yeah, I just wanted to double check.
True, but cosine of x squared is not something that's associated to integrate.
So it's not more than all.
Sine of 16 is a sine of 16. Just keep it as a sine of 16.
Sine of 16 is not a nice number.
You're thinking of, I think, 16 fine.
Typically, if you're ever trying to find cosine or sine of something, in radians at least, of something that doesn't have pi in it, it's not going to be nice.
That's a 0.
No, I still.
And then, but 0 has pi in it, it's
Just like,
True.
it's fine.
Alrighty, let's come back together and talk about this one. So looks like as I walked around the room, you all had a bunch of good ideas for how to approach this one. So, y times cosine of x squared. Anybody have a good way to integrate that with respect to x? Whoop.
Use the substitution where it is 1 plus cosine of 2x equal plus cosine of x squared.
1 plus sine of 2x?
Sorry, all over 2. All over 2.
So I think the issue with that is that might be cosine of x quantity squared as opposed to cosine of
Okay.
x squared. Slightly different, but that actually does make a slight difference. Otherwise, if the problem was changed very slightly in that way, then I think that would work and would be a good way to integrate. Unfortunately, I don't think we can integrate this as is. It's really hard to find antiderivative of y cosine x squared with respect to x. So what can we do instead? Jacob?
Integrate with respect to y first.
Integrate with respect to y first. Don't mind if I do. Yeah, so I think we can rewrite this region so that instead of having y going between two constants, we can have x going between two constants, and then that will allow us to integrate with respect to y before integrating with respect to x. Because this looks like something that's pretty easy to integrate with respect to y. It's y times constant. It's going to have an integral of 1/2 y squared times constant. So we're going to need to rewrite our set of points first so we know what our bounds are. So right now, y is going to go from 0 up to 2, and x is going from y squared up to 4, where x equals y squared is going to be this sideways facing parabola that we're only going to take the top part of since we're only looking at y coordinates going from 0 to 2. So how can we write this as x going between two different constant values? Okay.
0 to 4.
Yeah, just let x go from 0 up to 4 here. And how about y going between two different expressions, one of which I think is going to have x's in it? X? Square root of x to negative square root of x? I think that's close. I think the problem with that is that would give you area down here that you don't want to include if you go all the way down to negative square root of x. I think so. And then square root of x up here. I like it. Yeah, because if x equals y squared, that's the same as saying y is equal to plus or minus the square root of x. And we're only going to use the positive square root here because we're only looking at the top half of the parabola, not at the bottom half. So I think we can integrate from x is going to go from 0 up to 4, y is going to go from 0 up to square root of x. Okay, let's see. Hannah, how would we take an antiderivative of y times cosine of x squared if we want to integrate with respect to y? Yeah, I think so. The cosine of x squared term is just a constant, multiple, so it comes along for the ride. And integrating y will give us 1/2 y squared. So I think this is going to give us 1/2 y squared cosine of x squared. I agree. From 0 to radical x. We're going to plug in square root of x for y, and 0, I guess. Although that part's not going to matter, which will give us 1/2 square root of x quantity squared, cosine of x squared, minus 0 times cosine of x squared, when we plug in 0 for y, which, when we simplify, it's going to give us an integral from 0 to 4 of 1/2 x cosine of x squared. And how can we integrate 1/2 x cosine of x squared with respect to x? This one I think is actually going to be easier than the initial y cosine of x squared. Bob? Okay, what do you want u to be? We're going to let u be equal to x squared. Sounds good to me. Give myself a little bit more room. So if we let u equal x squared, That'll give us a du equal to 2x dx term. But we don't have 2x dx, we have a 1/2 x dx. So how can we rewrite? So if we rewrite to get 1/2 x dx on the right-hand side, what are we going to get on the left-hand side as our constant multiple in front of the du term? In other words, if du is 2x dx, then what should a 1/2 x dx be, Avery? It's going to be 1/4 du, which means we can replace 1/2 x dx with 1/4 du and then integrate with respect to u. We get an integral from x equals 0 to x equals 4 of 1/4 cosine of u du. We replaced 1/2 x dx with 1/4 du, and cosine of x squared just became cosine of u. Will, what are we going to get if we integrated 1/4 cosine of u with respect to u? Yeah, integrate cosine to get sine, so we'll get 1/4 sine of u, evaluated from x equals 0 to x equals 4. Tim, what do we need to do with this expression before we plug in 4 and 0?
Substitute x back in for u.
Yeah, we'll replace u with x squared. So we'll get 1/4 sine of x squared from 0 to 4. And I believe that's going to give us 1/4 sine of 16 minus 1/4 sine of 0. But since sine of 0 is just 0, I think that's going to be our final answer. Because sine of 16 is not a nice number. 16 pi, sure, that's something we could take sine of very easily, but 16 can't really be done. So just like our previous example, we don't know how to integrate this with respect to x. So instead, we swap the order of integration and integrate with respect to y first. And after we did that, we got an expression that we could integrate with respect to x, and that led us to our answer here. Where once again, in order to swap the order of integration, we needed to swap it so that we needed to rewrite our set so that instead of going between two constant y values, it went between two constant x values instead. Any questions or comments? Yeah, that's
I have a random question, but how does the calculator compute sine of 16?
Ooh, good question. How does a calculator compute sine of 16? So, if you take numerical analysis, you learn all about those techniques. But basically what a calculator will do is it has a bunch of techniques in memory, like Newton's method, and numerical techniques for approximating it. It'll say, I don't know what sine of 16 is, but I know how to find, say, sine of something very, very, very close to 16. Maybe 573,000 pi over 80,724, and use a bunch of different kind of little techniques to help approximate what this would come out to. By the way, if you want to use your calculator to approximate this, make sure it's set to radian mode and not degrees. If you do it in degrees, it's wrong because this is calc class. Calc class uses radians. Yeah, but basically, what exactly does your calculator do? That's a TI, Texas Instruments trade secret. But it uses kind of a bunch of numerical techniques. And if you want to talk to someone about what those techniques look like, because I don't know very much about them, admittedly, that's actually Dr. Webster's sort of area of expertise in the department. Will, do you have a question? Good question, though. I will say this, it's not that the calculator doesn't have memorized what sine of 16 is. It actually goes through and does kind of some behind-the-scenes number function to find out what something like that would be. All right, let's take a look at another one. And this one is not in the packet, but I want to talk about it anyway. Let's say we wanted to integrate this expression. Say we wanted to integrate from x equals 0 to x equals 2, integral from y equals 0 to y equals square root of 4 minus x squared. The square for our function is square root of x squared plus y squared plus 1. Integrate with respect to y. Integrate with respect to x. All right, Brianna. You know how to integrate square root of x squared plus y squared plus 1 with respect to y.
That would be the reverse chain rule.
Okay, so we would rewrite this as x squared plus y squared plus 1 to the 1/2.
Yes.
Not the easiest thing to do in the world, especially with that x squared plus 1 term. I think we could integrate this, but once we plug this in for y, it becomes very, very nasty very fast. Okay, not easy to integrate. We can swap the order of integration. Except, this isn't really any easier to integrate with respect to x than it is to integrate with respect to y.
Could you do a trig sum of both x and y to turn one to sine and one to cosine?
You could, but we're not doing trig subs in this class.
Okay, that's good.
Turns out this is not easy to integrate with respect to x or with respect to y. So we're going to have to do something else on this one. We're going to have to integrate it with respect to theta. Dr. Gerstle, I don't see any thetas there. So what we're going to have to do with this expression is we're going to rewrite this in terms of polar coordinates and replace our x's and y's with r's and thetas. And once we do that, we will be able to integrate an expression like this, but with using completely different variables than x and y. Speaking of which, standard 16 time. So standard 16 is going to be about how we can use polar coordinates in order to help us actually integrate expressions a lot easier. And now that I look at the time, there's like 4 minutes left. I don't know, I don't want to start a new standard. Y'all can go for this.
I heard that you can recite all the countries in the world. Is that true?
Yeah. Want me to do it?
Yeah, I kind of want you to do it.
Oh gosh, I'm a little out of practice, but let's see. Okay. Okay, Fiji, Samoa, Tonga, Tuvalu, Timor-Leste, Vanuatu, Kiribati, Papua New Guinea, Micronesia, Solomon Islands, Marshall Islands, Bahamas, Haiti, Cuba, Jamaica, Dominican Republic, St. Lucia, St. Kitts and Nevis, St. Vincent and the Grenadines, Bahamas, Barbados, Grenada. I got through the 3 Saints. Yep. So Trinidad and Tobago, Antigua and Barbuda, Canada, USA, Mexico, Guatemala, Belize, El Salvador, Honduras, Nicaragua, Costa Rica, Panama, Guyana, Suriname, Colombia, Peru, Ecuador, Bolivia, Uruguay, Paraguay, Brazil, Argentina, Chile, Cabo Verde, Sao Tome and Principe, Gabon, Equatorial Guinea, Maldives, Madagascar, Seychelles, Comoros, Morocco, Algeria, Tunisia, Libya, Egypt, Senegal, Gambia, Sierra Leone, Guinea, Guinea-Bissau, Cote d'Ivoire, Benin, Togo, Ghana. Let's see the top ones. So now next is Mauritania, Mali, Burkina Faso, Nigeria, Chad, Togo, Benin, Central African Republic, Democratic Republic of the Congo, let's see, Egypt, Sudan, South Sudan, Djibouti, Eritrea, Somalia, Kenya, Uganda, Rwanda, Burundi, Tanzania, Mozambique, Malawi, Angola, Namibia, Zambia, Zimbabwe, South Africa, Lesotho, Swaziland, Portugal, Spain, Andorra, Monaco, Cyprus, Malta, Liechtenstein, Iceland, UK, Poland, Ireland, France, Luxembourg, Denmark, Germany, Norway, Sweden, Finland, Russia, Estonia, Latvia, Lithuania, Belarus, Ukraine, So Czech Republic, Slovakia, Austria, Hungary, Slovenia, Croatia, Bosnia and Herzegovina, Serbia, Montenegro, Kosovo, Greece, Turkey, yeah, let's see, Taiwan, Sri Lanka, Philippines, Lebanon, Syria, Jordan, Israel, Palestine, Saudi Arabia, Yemen, Oman, Kuwait, Bahrain, Qatar, Iran, Iraq, Afghanistan, Pakistan, Kazakhstan, Kyrgyzstan, Uzbekistan, Turkmenistan, Tajikistan, India, let's see, Nepal, Bhutan, Bangladesh, Cambodia, Laos, Myanmar, Thailand, Vietnam, Malaysia, Indonesia, Australia, and New Zealand.
Nice.
Probably just one or two in there. 'Cause I haven't gone through them all. I'm a bit rusty.
We were talking about it yesterday. We were like, oh, someone hiding for top one. And they're like, he can do all the countries in the world.
Oh yeah, I did do that for them.
See it over
I just have a
yourself.
question for this one. I guess maybe I didn't make it clear, but I guess like I kind of did like the ones where I did each of them. So like critical points, I did that. Then extreme points, I did these, and then boundary points. Yeah,
So basically, yeah, this is where like I could see like yeah you could get that from that pretty self-explanatory. That I wanted to see some work on these.
Okay.
Because like I could sort of see like okay you're sort of taking derivatives but you're not making it clear like which
Okay.
image you're looking at.
Okay.
You have the right idea, but
Okay.
you weren't really showing your work and you had a few typos in there. So
Okay.
I think we could do that again on our
Yeah. Could I retest on this tomorrow, maybe?
Yeah, sure.
Okay.
Send me an email and we'll make it happen. Yeah, I do not foresee you having any issue getting into non-Euclidean, although non-Euclidean has filled up more than I thought it would. So we'll see.